Okay, problem number 1 on the May 4th assignment. I purposely put some problems on here. I kind of picked and chose some problems I haven't seen in a while that could show up. So these look familiar, but we got a little twist in here. So we got two different differential equations. We got this one, which is a normal separable differential equation. And then we have this one, which is also a separable differential equation, but I don't know if you remember, it's one of those really impossible ones to solve. It's actually called a logistic differential equation. dy dx equals ky times m minus y, which I'll talk about here in just a second. So the first one was just to find f. This one's f, so this was a straightforward solve a separable differential equation, which we've done a lot of, nothing new here. So I separated y's with y's, x's with x's. So I'm going to dy over y equals 2 times 3 minus x dx. So I integrated, got a natural log of y equals 6x minus x squared plus c. I use my initial condition. Y is 1 when x is 4, and I got a c equals -8. And then I just solved the y. I could have put c in at the end, or found c at the end. I just chose to do it right there because I noticed the natural log of 1 was going to be 0, which made it really easy. And then I just exponentiate both sides, so 6e to the 6x minus x squared minus 8. This is a logistic differential equation. You probably won't be asked to solve one of these because it's partial fractions and it's really horrible. It took me 3 pages in class, I don't know if you remember. But anything that looks like ky times m minus y, it's called a logistic differential equation. And we just know some things about it. These are really quick, easy problems, actually. One thing you know is it looks like this when you solve it. So if we were at a table to solve it, it would look like this, hence the term logistic differential equation, because it looks like a logarithm. It always has what's called a carrying capacity. It's like a population growth problem. The population can't pass anything. It can't pass that number right there, which in this case is 3. So it's got a horizontal tangent at 3 and it approaches 3. It also has an inflection point, concave up, concave down, at 1/2 the carrying capacity. So this first question said, find the limit as x approaches infinity of g of x. That's just the picture, that's the carrying capacity, that's 3. No math involved, no working, just bar. You can show a picture if you want. And then they ask for the limit of the derivatives. Remember, the derivatives are just slopes. So as we go towards infinity and function, that slope's approaching 0. In essence, the horizontal tangent, that's kind of there as the asymptote. And then the last part of that question, pretty quick too, was to find the inflection point and then find the slope at that inflection point. Sometimes they might just ask find the rate of the population change. It's the same question as slope. The inflection point's at 1/2 the carrying capacity, so it's 3/2. And they just ask for the slope at that point, so all I got to do is plug it into dy dx. It's 2y times 3 minus y. Y is 3/2. Put it on, I got 9/2. So I'm going to see another problem similar to this in this packet, but this is something we haven't seen in a while, so I want to make sure you got a peek at it before the AP test, which I guess for you guys will be next week. We'll talk more about that too.